What's that sound? Is it a truck passing outside? Somebody calling my name? Is that a bird? Good morning, everybody, and welcome to our science lesson. Now, my name is Nikisha Primus. I'm a teacher at the St. Joseph's Convent, Maraqua, and I teach integrated science at the Form 2 level and physics at the 3rd, 4th, and 5th form. Now, today's lesson is going to be about sound waves. Now, this lesson is designed for CSEC students, but students at the lower levels would be able to follow most of the lesson. So don't worry, I have you covered. Now, the objectives for today's lesson include: describe how sound is produced and propagated in a medium, relate the term pitch and loudness to wave parameters, and then finally we are going to investigate sound waves using cup and string telephone. Now, before we get into today's lesson, there are some things that you need to know. So, if you don't know it already, I'll just demonstrate briefly. First of all, you need to know that there are different types of waves. Now, these include transverse waves, longitudinal waves, pulses, and progressive or traveling waves. Now, I'd like to demonstrate each of these wave types. So I'm using a slinky, and I'll first demonstrate what is a transverse wave. Now, transverse waves are waves where the particles move perpendicular to the wave motion. So if the wave is moving from right to left, it will be going this way. Or we can do a up and down motion. So you'll notice that the particles are moving up and down. Well, you won't be able to see the particles, but the slinky is moving up and down. But the energy of the wave is actually moving from left to right. Now, for a longitudinal wave, instead of moving up and down, what we can do is pull and push instead. So if we do that, notice that the wave is moving along the slinky. So in this one, the particles are moving parallel to the wave motion. So that's a longitudinal wave. Now, for it to be a wave, it must be a continuous rhythm. So whether it's longitudinal or whether it's transverse. But for a pulse is different from a wave because it is a short-lived wave motion. So if it's a longitudinal pulse, it's just one, and you stop. If it's a transverse pulse, then you just do one up and down, and then you stop. So pulse, wave. So I hope that explains the difference between transverse waves, longitudinal waves, and pulses. Now, you may also see terms such as progressive and traveling waves. Now, these two terms are used interchangeably, and they just mean that the wave is carrying energy from one point to another, so from a source outwards. So all waves basically are progressive or traveling waves. Now, we will also need to understand some wave parameters, some terms often used in waves, and those terms include amplitude, wavelength, period, frequency, and speed. Now, on your screen, you would see a wave diagram that we use in math as a sine wave, or in science we use it as well, especially in physics. Now, I'll first define what is amplitude. Now, using this graph to explain what is a wave, we're going to use the x-axis as our resting or equilibrium position. So that's the wave without any motion. Now, the maximum displacement from the resting position or the x-axis is your amplitude. Now, notice that there is as the wave moves up and back down, it's a certain distance away from the x-axis. So that would be the displacement. But the maximum point it displaces, it is the wave's amplitude. Now, for that same wave, notice that on the first graph, we're measuring distance. Now, if the x-axis is measuring distance, then the point between those two top peaks, and those two top peaks, we call them crests, and the bottom ones we call them trough. So top, crest, bottom, troughs. Now, if you measure the distance between two successive crests, successive meaning one follow the other, then you're measuring the wavelength. But note that the measurement on your x-axis must be distance. You can also find the wavelength if you find the distance between two successive troughs as well. Now, if we were to look at the diagram at the bottom, notice that time is on the x-axis. When time is on the x-axis, then the distance between two successive crests or two successive troughs would measure period. Now, the period of a wave is the time it takes to make one complete oscillation. So the time it takes to make one full cycle, right? So the difference between wavelength and period is what is measured on your x-axis. If your x-axis measures distance, then you're measuring wavelength. If you're using time, then you are measuring period. Now, the frequency of a wave. The frequency can be defined as the time taken for, well, how many cycles or how many periods you get in 1 second. So if you have a lot of waves being generated in 1 second, you have a high frequency. If you have just a small amount of waves being generated in 1 second, then you have a low frequency. And then finally, we have to define what is speed. Now, speed, when it comes to waves, we use a formula, V is equals to F lambda, where F is the frequency and lambda, you can see from your graph, is wavelength. So if you know the wavelength of your wave and you know the frequency of your wave, when you multiply them, you will get the speed of the wave. Now, in order for sound to be propagated, you need a medium. When I say medium, a medium could be, when we talk about medium in science, it can be air, it can be water, it can be a solid, so solid, liquid, gases, basically. Now, without particles to vibrate, sound cannot travel. So in order for sound to travel, particles must be bombarded with that sound. It will cause them to vibrate. And when those particles vibrate, they will disturb the neighboring particles next to them and cause them to vibrate as well. And that process would continue until the wave travels from one end or the source to the other, which is the person hearing that sound. Now, in order for that to happen as well, those particles must be able to vibrate. And that's what I mean there by it must be sufficiently elastic. Now, if you have particles that can't move, it means that they can't vibrate. So they must be sufficiently elastic in order to carry the wave from its source to the person who is hearing it. So in order for it to move along or move through the medium. Now, we mentioned transverse and longitudinal waves earlier. That's why I defined them. Now, it is important to note that sound travels as a longitudinal wave. So the particles move parallel to the wave motion. And you should also note that sound cannot travel through a vacuum. Now, what is a vacuum? A vacuum is empty space, meaning nothing, nada, zilch. So there's no dust particles from the Sahara dust, no oxygen molecules, no carbon dioxide, nothing. So it's as if you're out in space, and those of us who watch space movies or follow the Science Channel, NASA, etc., you'll notice that in order to go out into space, you have to wear these special suits. And you wear these special suits because there's no air in outer space for you to breathe. So outer space is a vacuum. Empty space. Now, if it's empty space, it means that there are no particles to vibrate. And no particles to vibrate means no sound. So you can scream on the moon and nobody would be able to hear you. All right, so let's continue to this lesson of sound waves. Now, for those of us who are into music or who like to sing, etc., now you may have heard the term pitch and loudness before. But what's the difference? What is pitch? What is loudness? What is the difference? Now, the pitch of a sound depends on its frequency. See, this term came back, so it's important to know what is frequency. And just to remind you, remember that the frequency of a wave is the amount of wave you generate in 1 second. So when we talk about pitch, we are talking about the wave's frequency. So the greater the frequency, the higher the pitch. The lower the frequency, the lower the pitch. Loudness, on the other hand, depends on the wave's amplitude. Remember, amplitude, maximum displacement from the resting position. So the greater the amplitude, the louder the sound. The lower the amplitude, the softer the sound. And from the diagrams posted, we're going to use the middle diagram, the middle graph, as our original wave. And if we want a louder song, if we want to increase the loudness, you'll have to increase the amplitude. So notice that the wave is much higher than the one in the middle. So because the amplitude is greater, that song would be louder. Now if you want to reduce the loudness, you'll have to decrease the amplitude. So notice at the top right-hand side of your screen, you'll notice that the wave has a smaller amplitude. So that sound would be a softer sound. Now at the bottom, if you want to increase the pitch, it means you have to reduce the amount of waves being produced in 1 second. So notice at the bottom left-hand side of that diagram, you only have one complete cycle, one wave cycle. So that pitch would be lower than the middle graph because that middle graph has 2 cycles. So the bottom left graph has a lower pitch than our middle graph. At the bottom right-hand side, if you want to increase the pitch, notice you are generating a lot more waves within that same time period. So here you have 4 wave cycles within that same time. Therefore, you would have a greater pitch. So you want to make the song louder, increase the amplitude. You want to make it softer, decrease the amplitude. You want a lower pitch, then you decrease the period. And if you want to, sorry, not the period, the frequency. And if you want a higher pitch, like my voice, then you'll have to increase the frequency. Now we all know about thunder and lightning. We got a few of those, some of that a few nights ago. But did you know that thunder and lightning occurs at the same time? Maybe you did, maybe you didn't. Now the reason why you would hear the thunder long after you would have seen the lightning is because of the speed at which light and sound travels. Now light travels at approximately 3 by 10 to the 8 meters per second. And for the little ones to understand, that's 300 million meters per second. That's extremely fast. And for those of us who watch Flash, not even Flash can run that fast. And the speed of sound, however, is only 330 meters per second. That is like the total compared to Flash. So sound travels way slower than light does. And because of this, you would always see lightning long before you actually hear the thunder. And that is why you always see lightning first, and then a while after, you would hear the thunder. Now, you can use this information to estimate how far away a storm is from you. So if you want to time the length of time between when you see the lightning flash and when you hear the thunder, you can use that time to estimate the distance using the formula. Speed is equal to distance divided by time. You just have to rearrange it to make distance the subject of your formula for our senior students. Now the activity for today's lesson, because no physics lesson should go without an activity. So we're going to make a cup and string telephone. Now some of us would have done this activity when we were younger. Maybe you went to summer school or camp and they would have done this activity. For those of you who haven't, I'll introduce the basics first. And for those of us who think we're too old for this, don't worry, I will step it up a notch once I've got the basics out of the way. So what you'll need for this, 2 plastic cups, 2 disposable cups. It could be any size once the cups are the same size. So make sure that both cups are of equal size. You'll also need some string. So I'm using nylon today, but you can use whatever string is available to you. And you'll need something pointy like a pin, I'm using a compass from a geometry set because I think that it's ideal. Now, if you're young, if you're less under 10, you may need a parent or guardian or an adult to help you with this. So the first step, now the next step is to take one end of your string and push it through the bottom. So I hope you can see, right? So you push it through the hole you just made. Pull it and make several knots to make sure when you pull on the string, it would not pass back through that hole. So you can make about 3 or 4 knots should be fine, depending on the size of your hole. Try not to make your hole too big or the string, you'll have to make a lot of knots. Let's test that. Okay, that's fine. So that's one end done. My string is very long because when you're playing at home with this, you want to see how far. You would want one person to be maybe in a bedroom and the other person in the living room, for example. So you would want your string to be long. But the disadvantage with that is that it can get a bit tangled like this one, right? So let's just clear that up a little bit, right? And we take the other end and we push it through the bottom of the other cup. Pull it through just like before. Make several knots just to make sure that the string would not pull through. So I'll just make 3 knots so that it would be secure. Right, and that's fine. And we're ready to go. As simple as that. We have a cup and string telephone. So what you'll do, one person, your friend, your little sister, brother, whoever it is, mommy, daddy, uncle, would hold one end of the cup. You would take the other end. Now you would have to decide who's going to speak first and who's going to listen, because both persons can't speak at the same time because nobody will be listening, and both persons can't have it at their ears because it means nobody will be speaking and then you won't be able to hear anything. So you need to decide who's going to go first. Now, one thing with this is that when you're doing it, you have to make sure that the string is turgid, meaning it should be straight. So try not to have it sagging. So you pull it so that it is stiff. You have one friend, listen, one end, and then you speak into the cup. Well, the other person would speak into the cup at the other end, right? And you would let me know via comments if you're able to try it at this point, or you can send in your comments afterwards if it actually worked. And I can guarantee that it does work. The person who is speaking, you just have to make sure that you speak clearly, right? You don't have to shout, just make sure you pronounce your words clearly so that the other person would be able to hear. So that's the simple version. Now, for those of us in Form 4, Form 5 who thinks, oh, that's a baby activity, I don't want to do that. Now, I use this experiment for my CSEC class, and what we do is that we can investigate 2 things. We can change the thickness of the string. So I was trying to get different thickness nylon, but I realized that that is very difficult to do. So you can, if you get 2 or 3 different thickness nylon, you can do the same setup, carry out the same experiment using these 2 same size cups. Now these are 9-ounce cups, but you can use smaller ones or larger ones. Once they're both the same, change the thickness of the string. Carry out the experiment the same way, but this time, instead of speaking into the cups, because we can change our tone of voice from one activity or one trial to the other. So to remove that variable, what we can do is just take a device such as your cell phone, a laptop, or a tablet, or a radio, something that can play either a note or a sound, whatever it is. And instead of speaking into one end, you will play that song in one end of the cup and have somebody listen at the other end, and you can compare the quality of the song produced when you vary the thickness of the string. So that's a very unique, a very interesting, thing to find out. Now, if you can't access different size nylon, if that is difficult, another twist to the experiment is to change the size cups. So These cups are easy to find. They're relatively cheap in the supermarket. You can buy 3 different sizes, maybe a 7-ounce, a 9-ounce, and a 12-ounce cup. So what you do, keep the string and change the cups, and then compare to see if the quality of the song produced varies. All right? So you can try that out and let me know. All right, so we stepped it up a notch already. I went through all that. So we have some questions. Well, I have some questions. So are sound waves transverse or longitudinal? Are sound waves transverse or longitudinal? So I'll just pause for a few seconds. All right. Now, you said that sound waves are longitudinal. You are correct. Give yourself a clap. The second question, can sound waves travel through a vacuum? Can sound waves travel through a vacuum? So pause again. Now, if you said no, you are correct. Sound waves cannot travel through a vacuum because you need particles to vibrate. Next question. If you want to increase the pitch of a sound, should you increase the frequency or the amplitude? If you want to increase the pitch of a sound, should you increase the frequency or the amplitude? All right, so you should recall that pitch would affect the frequency, so you should increase the pitch to increase the You should increase the frequency, to increase the pitch. And finally, does the type of medium affect the way sound travels through it? Does the type of medium affect the way sound travels through it? Now, this one I'm not going to give you the answer to because I want you to carry out the experiment yourself. Somebody had a question. They wanted to know, does it work? Well, Ezra Brown, try it out and let us know. All right, so we're getting ready to wrap up. So what did we learn today? You should have learned that sound is a longitudinal wave. You should have also learned that it needs a medium to travel, so it cannot travel through a vacuum. You should also remember that sound travels at a speed of approximately 330 meters per second in air, unlike light, which travels at 300 million meters per second. And finally, you should know that sound waves behave differently according to the medium or the material it passes through. And that is why when you're at the beach and you're underwater, person speaking, it would sound a little bit more muffled when you're underwater as if you, except if you're above water. So carry out the experiment, and then you can leave your comments after, and you can tell us if it worked, if you enjoyed doing it. I hope you guys had fun with this lesson. I surely did have fun. Thank you for tuning in. And remember, science is fun, can be fun, will always be fun. Have a good day.
Good morning, students. We are here this morning for our science lesson that is going to be vertebrates. Before we start our lesson, we are going to get a little active. I want you to get up out of your seats and stand up as we do the actions to Tony knows that I love you. Okay? We're going to do the actions. So let's go. Tony knows that I love you. I love you. I love you. Tony knows that I love you. I love you. Let's do it a little faster. Tony knows that I love you. I love you. I love you. Tony knows that I love you. I love you. Now I know a lot of you got mixed up and you touched your toes for your eyes and your eyes for your knees, but it's okay. That's just to get you started. Okay, my name is Mrs. Tamesia Smith-Johnson, and I'm going to be doing your science lesson today. Now for this lesson, by the end of this lesson, we are going to be able to define what is a vertebrate. We're going to list the 5 classes of vertebrates, and we're going to describe the main features of each classes of vertebrates. What is a vertebrate? Now, a vertebrate is an animal that has a backbone or spine. And as you can see in the little corner there, it's showing on us as human beings our spine or our backbone. The spinal cord is the nerve, and the bony part of it is called the backbone. Now, can you remember what we just said is a vertebrate? Can you use that definition to try and tell us what the 5 classes of vertebrates are? Okay, let's see if you got them right. We have mammals, we have reptiles, we have birds, fish, and amphibians. Next slide. Let's talk a little about mammals. Now, mammals have hair or fur. Can you think of an animal now that has fur or hair? They have mammary glands that produce milk. Most often, sometimes we call them breasts. They are warm-blooded, and they give birth to the live young. Now I wonder, think of yourself. Let's think of ourselves for a minute. Do we have any of these characteristics of mammals? Then maybe we are mammals as well. Next slide. Now, here's some fun facts about mammals. Did you know that some mammals live underwater? Yes, we have mammals that live underwater. They have a thick layer of blubber or fat that helps them to stay warm. However, even though they live underwater, they have to come to the surface in order for them to get oxygen to breathe. They store their oxygen in their blood and in their muscles. Yes, they have blood. You are a mammal, you have blood, so they have blood too. They have blood, however, they have more blood than those mammals that live on land. So they probably have more blood than you. Next slide. Let's talk about birds. Oh, those birds are beautiful, aren't they? Now, I love birds. Do you love birds? I believe you'll say yes. All birds have feathers. All birds have wings. Now, what do you think they will do with those wings? Yes, they probably fly. But do you know not all birds can fly? Tell me one animal or one bird that have wings but can't fly. That's right. Maybe a fowl, as we may say, a hen. Yes, they have wings, but they can't fly. All birds have beak. That's what they use to eat. All birds lay eggs, except for the obvious male birds. Male birds can't lay eggs, only the female birds can. Next slide. Now, reptiles. Oh, it crawls my blood to speak about reptiles. Let's talk about it though. Reptiles are cold-blooded animals. This means that they cannot control their own body temperature. All reptiles have scales and dry skin. Yes, they have scales, but they're not fishes. Most reptiles produce eggs, while some give birth to their live young. For example, some snakes lay eggs, some don't. Some lizards lay eggs, but some don't. Most reptiles are found on land. However, there's a few that live in the sea or in water. They breathe through their lungs. Yes, they have lungs just like you and I. Now, let's do a little activity. Let's pretend we are living underwater. How many of you like to go to the sea? I sure do. Let's hold our nose for 10 seconds. Pretend we're under that water and see how it feels. Let's go. We're counting. All right. How did that feel? Whew, I sure felt tired. My oh my. Now, which animal do you think we're going to talk about next? Or which class of vertebrate do you think we're going to talk about next? Let's see if you're right. Ah, that's right. We're going to talk about fishes. Yes. They have a skeleton, they have bones, they have a backbone. So they are classed as vertebrates. Now, all fishes are cold-blooded. And remember what we said about cold-blooded animals? That's right. They cannot control their own body temperature. So they're cold-blooded. Yes, they live underwater, but they're not mammals. Remember we said that some mammals live underwater? No, they're not mammals. They're classified now as fishes. They use their gills to breathe, so they won't have nostrils like us. Instead, they have what you call a gill. Fishes have fins. Some species or types of fishes have scales, while some do not. Can you remember which other class of vertebrate have scales? Yes, that's right. They're reptiles. Now, fishes live in water. Some are freshwater fishes, while some live in the sea, which is salt water. Let's talk about amphibians. Now, I don't like reptiles, and I don't like amphibians. They're pretty much scary to me. I'm not sure if they'll be scary to you, but let's find out a little about them. Amphibians live both on land and in water. Now, their body is covered with slimy and slippery skin. That means you can't easily reach out and catch them. They can slip away from you. They are cold-blooded animals. Some have 2 pairs of legs that they use for making long jumps.
The amount of waves being produced in 1 second. So notice at the bottom left-hand side of that diagram,